Hey guys, and welcome to a new week of Sliceform, where this week we're going to be going over computer-aided manufacturing. So for this week's project, we are going to be making a longboard. Very similar to a skateboard, but obviously much longer, and it's a much more comfortable ride. But it's a really good computer-aided manufacturing project because although you can mass manufacture them, a lot of them are actually still hand-built. They're very, very popular in Southern California to ride up and down the boardwalk and all piers, but they're a really fantastic project to get into CAD and transition to CAM. That's what we're going to be focusing on today. How can we take a robotic machine, something like a CNC, which we'll be going over later, and figuring out how to give it instructions so it can actually manufacture perfectly exactly what you want to make. Now, a longboard is a really good project when you're going from CAD to CAM, because yes, it is still a woodworking project, but it's got a bunch of manufacturing steps where you could do it by yourself, by hand, but they're really, really tricky. For example, the symmetric profile of the entire board is really hard to do. Putting the holes for the trucks to screw into is really, really hard to do, to get it exactly mirrored and exactly in the right location. And so the two sets of holes are dead on top of each other. Very, very tricky. So this is why we're going to be treating this much like in a manufacturing environment where, yes, some of the processes have done before, some of them will be done afterwards, but all of the tricky parts we're going to be leaning into the CNC part of. Now, a CNC machine, also known as a computer numerical control, is essentially just a robot that can make stuff for you. It is incredibly similar to a 3D printer, but instead of having a nozzle that squirts out plastic, you've now got a cutter or connected to a motor that can actually carve away lots of material. So instead of it being an additive process, it is a destructive process. Now, for a long time, CNC machines were just ridiculously expensive, talking tens of thousands, and really the only way to have access to it was either you worked at a company that had one, you built them yourself, or maybe you had one on your university that you were able to play around with. But now you can get CNCs for maybe $1,000 to $2,000, and there's actually lots of kits where you can build it yourself in the exact same realm or in the exact same level of difficulty where people actually start to build their own 3D printers from scratch. Now, diving into the CAD software of this class, we can actually make our lives a heck of a lot easier by making this entire project with a top-down view. Basically, most CNC machines have a cutter that is pointing downwards. Sometimes you can have a horizontal, but they're nowhere near as common. And so by building something with a top-down or eagle-eye view of the project, it's going to make it a whole lot easier. If you decide to make this, well, on the right or the front plane, it is going to be really confusing when you go into the CAM software. So very similar that you would do in other manufacturing processes where you have some type of real world dictating how you design it. That's exactly what we're going to do for here. We're going to imagine that we are going to be looking straight down on our part as if we were the cutter, so we can actually envision what the machine will do. And this is going to help us out a lot when we transition from CAD to CAM, and it's going to be even more helpful when you transition from CAM to the real world CNC machine. Now, to start off, we are actually going to be going into our document settings up here in our browser and verifying that our units are set to inches. If you have them in millimeters, go ahead and change them over. This is a really important distinction right now because most CNC machines, much like 3D printers, require all of their code to be put into them in millimeters. That means that we can do all the design, all the CAD work in millimeters or inches, whatever we'd like, and we can do all of the CAM portion in millimeters or inches, doesn't matter, but anytime we're going to be exporting or post-processing, we need to make sure that it's set in millimeters. Now, we're going to be starting off by making a brand new sketch on the top plane, and we're going to be making a very simple rectangle that starts from the origin and goes to the upper right-hand portion. We're also going to be highlighting the whole thing and hitting X so we can turn this into a construction rectangle. And we are going to be dimensioning this so it is 4 inches wide and 33 inches tall. This is basically going to be our bounding box of exactly how large can the profile fit inside it. Because we want to have a symmetric profile, we're actually going to be building half of it inside this boundary and then mirroring it about this middle vertical line. That's going to make life a lot easier. Having a total width of 8 inches is about right for longboards, and 33 inches is usually on the smaller length. Usually they start from 33 inches and can go really as long as you'd want. I've made a longboard for a client that was 72 inches long. So you can go crazy, but usually 33 is a good transition size between people that have got skateboarding experience and want to then go into longboarding. So we're going to be starting off our profile by making a 3-point arc that starts from our origin and goes up and to the right. We are going to be adding a dimension from the origin to the end point, and this is going to be 2.25 inches to the right and 1.25 inches upwards. And we also want to make sure that the center of this arc is also coincident with this vertical construction line. And then going to the top of the board, we are going to be making a 3-point arc that starts from that top left corner and it goes down and to the right. And this wants to be dimensioned to have a 1-inch radius, where the end point is 0.75 inches from the top left-hand corner. And we also want to make sure that the center of this arc is coincident to that vertical construction line. And then going back down to the bottom of the board, I'm going to be adding a line that starts from the end of my arc and just goes up and to the right. This end point right there wants to be 12 inches upwards, and it also wants to be 3 5/8 from the origin. That would be 3.625. And then to join those two endpoints, we are going to be adding in a fit point spline. And just like we've done in the past, this doesn't need to be a very mathematically rigid arc. This just needs to look about right. This is where you have that design bone in your body that you're going to be using. So you can select the end point of that line that we just made, the end point of that arc, and then instead of hitting enter, just go ahead and click that little green check mark. And this is where we can start to adjust all of these lines as well. So move it around and make sure it is about looking right. And this is where we can help out our design just a little bit by tacking on some tangent constraints between the spline and that top arc. And this is where we can kind of pull and prod at all these vertexes till we get an arc that doesn't pass outside of this line, like you can tell this one does, until it looks, well, like a longboard. If it doesn't look quite right, then you can always kind of mess around with the spline. So work it until it looks good. We can finish off this arc by adding a fixed constraint to that, so it turns green, so it won't be able to move around. And this is also where we can put in our holes on the very top and the very bottom. We need 8 holes total, so we need to have 2 on either side of our mirror line. So we can go ahead with our circle tool, and we can just make 4 circles, 2 on top and 2 on bottom. By highlighting all of our circles, we can also add on an equal constraint to all them so they're all the same size. They want to be 3/16 of an inch in diameter. And we also want to make sure that they're all exactly on top of each other. So go ahead and hold down Control and then select the centers of all of these circles and then add on a vertical constraint to them. We also want to say that the distance between the center of the circle to that midpoint wants to be 0.8125. And then the distance between both of these holes on the top and the bottom wants to be 2.5 inches. That's the standard distance for old school trucks that you'll find on longboards. And we can also say that is the same distance from the bottom point to our origin. And you can do the exact same dimensions up on top, where we can say the distance between the 2 circles are also 2.5 inches, and the distance from the top of the circle now to the top of the arc is also 2.5 inches, and that should make them all constrained. Now using my mirror tool up top, I'm going to be highlighting the entire sketch, and I'm going to select the mirror line because I can't mirror the mirror line itself. That has to be unchecked. Then I can move over to my dialog box and select the mirror line, then go back and select it on my sketch. And you can see the other side is giving me a preview, and we can just click OK. That looks perfect. Now we're going to be finishing that sketch and going and extruding it upwards. This is going to be a value of 0.54 inches. That's kind of the tried and tested value where it has a good amount of thickness that it's not going to break on most people, but it is thin enough that when you stand on the board, it does have a little bit of flex to it. So let's just hit OK, and you can see we also have some sharp corners right there. So you can just go ahead and add in a 1-inch fillet to both of these lines. 1 inch and hit OK. And that just softens out any of the corners, which is nice. Because the board is going to be attached to our trucks with some countersink bolts, we also want to be adding on some chamfers to all of our holes. So just select all of these, and this is going to receive a 0.125 inch chamfer, or 1/8 of an inch. There we go. And then just to make it look that little bit extra, we can just add on a very simple wooden finish. Bamboo always looks kind of cool. There we are. Now, going back to design, if you say this is done in the real world, you're actually missing quite a few steps. If you look at the side profile, you can see that all of the all the edges here, they have really sharp corners between the top and the edges. That's really not comfortable to ride, it's not comfortable to hold, and as we know from old manufacturing, sharp corners is where things break first. So even though we are going to be leaving it here for the cam portion, in real life, these edges would actually be routed out. And this is where CNC kind of shines. I know a lot of people think, oh, it's a robot, it can make everything. And that's really not an efficient way to approach this project. The CNC is really fantastic at making very accurate and very reproducible cuts. Where it doesn't excel is when you need to constantly do different tool changes over and over and over again. You need to flip parts over and over, and it has so much inefficiencies built into it. When you can say, hey, these operations of the project work really well for CNC, but these operations don't, and it's usually a lot faster if a human being does it, then that is the next step of manufacturing, where you go, hey, I'm going to be spending less time if I do this by hand than if I give this job to a CNC machine. So just going back to this project, there are some steps that would make this a finished design that we are not going to be adding into there. We are purely going to be doing the CNCing that CNCs do best. With that said, we are going to be going from the design portion all the way down to our manufacturing area. And as you can see, we have a brand new set of tools. For a lot of people, this is quite intimidating. Don't worry, for this class, we aren't going to be going over too in-depth about all of the different tools and processes and terminologies. Being a CNC manufacturer or a CNC operator or a technician is its own profession. It is absolutely a whole branch of engineering that requires knowledge of the different materials, different cutters, material physics, different types of manufacturing, and how you can do things most efficiently for your client or whoever you're manufacturing this for. So we're just going to be touching over some of the simple things within this project today. For example, the setup section, this is how we're going to be defining our material that we're actually cutting away, the larger kind of vague block of wood that we'll be carving this out of. The 2D area is for any 2D operations. The 3D is for any 3D operations, so very complicated curves. The drilling is just for drilling out holes. We'll be doing a little bit of that today. Multi-axis, that's for machines that have got all different ways that they can go in from X, Y, and Z, and all the rotations as well. We won't be touching over any of that. The actions, we will be touching over this. This is how we're going to be simulating how our cutter is actually producing it, and then post-processing it so we can actually send it to a CNC machine. And then the manage area is where do we have all of our tools, or all of our virtual tools, some of which we're going to be making today so that it can actually cut it out in real life. So the things that we'll be working on today are going to be developing that stock material that we can cut it out. Then we're actually going to be making 2 brand new tools from scratch. Then we can start all of our drilling and countersinking operations that we'll have on our drilled holes. Then we can cut out the outer profile where it's completely out of the frame. Then we're going to be simulating all those cuts so we can actually double check exactly what we're doing. Then we'll be post-processing it out so it can be worked by a CNC machine. Now we're going to be starting off this cam portion by going over and changing our units from millimeters over to inches. Because all of our tools are going to be in imperial and fractional units, it's going to be a lot easier if we design this as if we're working in inches. So with that in place, we can now work on a new setup. So go into the setup menu and then select new setup. And when you do that, you can see you've got this kind of faint yellowish box all the way around your part. This is the stock. This is the large bit of either wood, metal, foam, plastic, anything that you're working on that you can then find the project inside that volume. So we'll have a couple tabs that we'll be working in. The setup, this is where we can essentially put our origin or our datum point. This is where everything is basically based off when you're working on your project. You can see there's little white tabs or little white dots on all the corners, in the middle, on all the edges. We can essentially select where the origin is anywhere on this project. But for most CNC operations, I'm actually deciding, do I want my origin to be on the top or on the bottom? Now, because we are working on a project that needs to be cut all the way through, and the very bottom of our cutter actually wants to be cutting ever so slightly lower than the underside of our board, just so we can verify that it's cut all the way through, then I usually want to make my origin on the very bottom. But if I was doing an operation like engraving on the very top surface, I don't care how low down or how thick my board is. I just want to make sure that I'm basing everything off of the top surface. So in that case, I would actually want to select the top corner. We can essentially choose any of the corners on either end. It doesn't really matter too much to us, but remember that most CNC machines are actually rectangular shaped, and I'm usually standing on one corner. So whatever makes sense for your machine, go with it. It doesn't really matter. For me, most CNC machines that I've worked on, the bottom front left corner makes the most sense. But if it has any changes for your CNC, absolutely work around that. Now moving over to our stock tab, this is where we can define the size or the volume of this yellow stock box, essentially. Currently it's set to relative size box, so it's saying, well, I know your project is 8 inches by 33 inches, so let's add on 0.04 or 1 millimeter. That's the kind of standard. And for us, we're saying, well, that's just not enough. We need to add on a little bit more, but how much do you need to add on is the question. Very often, if I'm doing a woodworking CNC project, I already know the size of my board because I cut it. So it may be easier, instead of doing a relative size box, to do a fixed size box. This is where we can enter in the X, Y, and Z dimensions of our box itself. Now, because we're going to be using a pretty standard 1/4 inch end mill for this project, and it has a 1/4 inch diameter, obviously, we can actually say, well, I know it's going to be carving away 1/4 inch on either side. Well, we want to have some material left over as kind of a frame, so everything doesn't get kind of jostled around. So let's add in 1/4 inch and then another 1/4 inch for material on both sides. So instead of 8 inches, we're going to be making this 9 inches wide. For the length of our board, we're going to be changing this from 33 to 36 inches. That's just handy just because it's a very standard length of lumber. And if we get a top-down view, you can actually see that we've now got a good amount of area in these top and bottom corners where we can actually drive a screw through our wooden board and secure it down to our spoiled board where we're actually going to be carving this. If you don't have any area for your screws to actually mount it down, then your cutter may actually run into the screws and then you can end up with broken tools, a ruined project, and it's also kind of dangerous. So adding on just a little bit of extra volume so you know you can very safely secure down your piece is always going to be a good idea. We're also going to be adjusting our height to be 0.54 inches, the exact same dimension as our thickness, just because in this manufacturing process, before we got to a solid board, we would usually be planing it down to the right thickness. With that in place, we can just hit OK, and we have now got a finished setup. Now for this project, we're going to be needing 3 tools to actually make this shape. We're going to be needing a drill to cut out all of our holes. We're going to be needing a countersink bit to make all of our countersinks. And then we're also going to be needing to make an end mill that can actually carve out the entire profile of our longboard. And to do that, we need to basically group all of our tools in what's called a tool library. Now, if you go up to the Manage tab, you can see that we do have a tool library. Fusion has actually got a gigantic list of some pre-made tools, things like probes, different tools in metric, taps, turning stuff, it goes on and on. There's a lot of pre-made tools that are really, really handy, but for today, we're gonna be making 2 of them from scratch, and we need to put them in a very convenient area. So for a lot of my CNCing work that I do, especially in woodworking, I've actually got my own folder where I've got some of these tools that I use constantly, already pre-made. So to make this kind of area, we're gonna be making a new folder just for you in your cloud category. That means that if you ever go to a shop where they have a CNC machine, but they've got a computer already rigged up to it, you can just sign into your account and all of your tools that you make today, they're already in the system. So we're gonna be clicking on the word cloud and then right-clicking it and then saying, I would like to make a new library, and we can just say this has my custom tools. Now we have a blank void in here, and this is where we can start to add in some of our tools. Now we'll start off by making a 3/16 inch drill bit, and to do that we need to click this little plus sign at the very top of our screen, and this is going to give us a big list and saying, hey, what tool are you making? Well, we're going to be making a hole making tool, because it's a drill, and conveniently there is a drill icon right here. As you can see, there's lots and lots of different ways to make drills, probably more than you ever thought. So let's click the drill tool. This description, we can just call this a 3/16 inch drill, nothing too fancy. This is where a lot of people put in all the very specific vendor codes and exactly where did they purchase this, just so they have a bit of a paper trail with this. In our cutter, this is where we can type in all of our information about the actual size of this. For example, you need to know exactly what is the distance between the very bottom of your drill to the top of your cutter, so that you know, hey, if I say to drill this 6 inches deep, but that distance is only 5 and a bit inches, then it's going to end up breaking my machine. So I need to know all of these bits of information so that I don't destroy my project or destroy the tool itself. So from our packet, you guys can type in all the information into this section right here, so you can basically make a drill bit that you can find in real life. So there we go, we have all of the dimensions of our drill bits, and we also want to be going into the cutting data tab, and this is where we can type in all the information about exactly how fast is it spinning, how fast is it moving when it's in the CNC machine. So unfortunately, most drill chucks that we have, which is the tool that can hold onto our drill bit, are actually really heavy. And when you try and spin really heavy tools at max speeds, things can be really dangerous. Things can just kind of blow up and destroy themselves. So usually when you have a drill bit in a CNC machine, you're not limited by how fast can you spin the drill bit, but by its holder. So for a lot of reasons, the spindle speed is actually limited to about 5,000 RPM, or 5,000 revolutions per minute. What we can say is the vertical plunge rate, it wants to be set to about 40 inches per minute. This is exactly how fast is it going down. Now, most of these values are actually preset for drilling into metal, which is much harder than drilling into wood. But in this case, we're just being a little bit more conservative with our speeds. I'd rather drill something a little bit on the slower side of life rather than drilling too quickly. We're gonna go and hit accept for this, and you can see our tool is right in there with all of its information down below. Now we can make our second tool for the day, which is going to be an end mill with a flat bottom. End mills are basically just really large drill bits that are just used instead of drilling out holes, but for actually carving linearly out a lot of material. The underside is a good classification, so if you have a ball end mill, then it means it's a complete hemisphere on the very underside. If they just have little radii on the corners of them, but it still has a flat bottom, then it's called a bull nose end mill. But if it's just flat with corners on the bottom, just like a cylinder essentially, then it would just be called a flat end mill. So let's click that. And this is going to be a 1/4 inch end mill. 1/4 inch end mill is kind of the bread and butter. It's the tool that a lot of CNC router operators reach for. It is relatively inexpensive, it can do a lot of work, it's thick enough that it can be really strong and stable with some really fast cuts, but it's not so large of a diameter that you can't get relatively sharp corners, because anytime you're doing an internal CNC job, you can never make perfect internal corners. And then again, we're going to be going into our cutter tab and then typing in all the information that you guys can get from your packet. And then going into our cutting data, this is where we can put in all the information about this cutter. So our spindle speed, or how fast is it actually rotating, this is going to be set to 23,000 RPM. Our cutting feed rate is going to be set to 368 inches per minute because we're cutting a much softer material than metal, that's why it's set so low. And then our plunge feed rate is going to be set to 92 inches per minute. We're not going to be going over all of these, all the mathematics behind this in this class, but we'll be doing it in the next one. So just go ahead and type all of these in and then click accept. So now with our tools made, we can actually start to work on all of our operations. And the order of our operations is actually really important. If we do our carving out the entire thing first, then we're not leaving a ton of material to actually hold it in place. And if we have any drilling or any countersinking that has a twisting motion, it's actually going to be twisting our board and our frame with it. So if we do all of these kind of twisty, torquing operations first, then carve it afterwards, then it means those points within our geometries aren't going to be moving around. They're already made. So we'll be starting off by drilling our holes, then countersinking them, and then carving out the outside. To do our drilling, we can just select our drilling tool. And this is where, because we have our tool already pre-built, it'll do a lot of the work for us. We can go and select, go into our custom tools, and you can see, well, there's only one drilling tool, and that's our 3/32 of an inch drill bit. So we'll just select that, and you can see all of our speeds and feeds that are already built in place. So I'm just going to be going over to the geometry tab, and this is very, very simple. It's saying, what are the holes that you're trying to drill out with this tool? Well, we have 8 holes to drill out, so we can just zoom in on our project and just select all of these surfaces. And when I do this, you can see that I've got little yellow lines joining them, and I've got a red down arrow and a green up arrow. The red down arrow is basically saying, where is it entering? And all of these yellow lines are our links. So it's going to be going down, moving back up, going over, drilling out that hole, going down. And then as soon as it gets to this last hole, it's going to be coming out because it is now done. That's not the case for us because we also have some more holes up on top. And you can see that little yellow line linking it from the others. Perfect. So it's going to be starting out on this bottom corner and then moving over to this. And as soon as it's done, that's the end of that operation. Moving over to the next tab, which is called height, we can actually say exactly how high or how low are things set. Usually this is already worked out by the computer and it's really efficient and there's nothing much to change. But in our case, if we have a side view, you can see that our drill bit isn't actually drilling all the way through. The very tip of the drill bit is, but we need it to go all the way through. And that's really more concerned about the bottom. And luckily enough, in this little dialog box, you can see we have a bottom height. And I'm going to go ahead and check this, this little section that says drill tip through bottom, and you can see that it is now going all the way through our piece, which is exactly what we want. We can also go into our cycle process, but there's really not much going on here. This is just saying how is it going in and coming back out. Drilling rapid out is perfectly fine for us. So we can just click OK, and as you can see in our browser, we've got this new process popped up. If we want to, we can actually run a simulation and see exactly how all this is drilling. So in our actions section, you can see we've got a simulate tool, and if we hit play, let's slow it down a little bit. If we hit play, you can actually see exactly how is our drill bit cutting away our material. There we go, and then it's going to be moving all the way over. Speed up just a little bit. And then you can see it'll be drilling the rest of our holes, and then it is perfectly done. And we'll be going over all of these settings right here in a little bit, but just kind of more importantly, you can see this entire operation is only going to take 25 seconds. That's pretty short. That's great. So with all of our drilled holes already done, we can now countersink all of our holes. And this is where we can use one of the pre-built tools that's already in Fusion, which is really nice. It means we don't have to make a thing. So let's go into our drilling section. For our tool, this can actually be found within the Fusion 360 library. So we're going to be going all the way down to tutorial inch, and you can see we have our countersink bit right there. And if we select it, you can see we've got all of the dimensions and speeds and feeds and everything already built in we don't have to do a thing. So let's just select that, and going into our geometry, we can now select all of our hole faces. And that is going to be the angled heads just above all of our holes. We've got 8 of them. And this is a really good area where you can say that, well, because we already have the defined location of all of our holes, it's going to be a lot easier to go drilling with the drill bit and then countersinking rather than the reverse. Because this is an angled cut, we actually don't need to mess around with the heights whatsoever, nor do we need to change these cycles. So we can just click OK, and now we have our own cutter. And this one actually has the tool holder built into it as well, which is kind of nice. Now moving on to our last process, we're going to be cutting out the entire profile of our board. And this is going to be using a 2D tool because we're actually not moving our cutter up and down around curves, it's just following a 2D profile. So we can expand the 2D menu and we're going to be clicking 2D contour. Very, very easy tool. So it thinks that we're using the Countersink bit, which we're obviously not. So let's change that over. We're going to go back into our custom tools, and this is going to be using the end mill, the 1/4 inch end mill. And for our geometry, we're actually going to be selecting not the top, but the bottom profile. This bottom edge, you can see it's highlighted in blue. Now, an important geometry within CNCing is actually putting in a couple tabs that you can check in this little dialog box. Now, a tab is just a really small, thin little bit of wood or whatever material you're working with that actually holds the project to the outer frame. Because as soon as it's done cutting all the way through, your board or your longboard is now just floating inside, and if it wants to, it could rotate or smash into the bit and then it flies out. It's very, very dangerous. So make sure anytime you're doing any woodworking, even though it takes just a little bit longer to do some post-processing, adding in some tabs is going to be just fine. This tab distance of 2 inches is kind of small, so let's increase that. So let's go to something like 6. And if we zoom in, you can see that we have these little tabs right there. They're only small bits of wood. You can actually cut them away with just a really simple chisel hit. But putting them in there is absolutely essential. We can also go into our height tab, and we really don't need to mess around with this whatsoever because we can see our very top is going to be lined up with the top of our material, and the bottom is selected to the 0 point or the very underside of our board. That's fine. Going over to the passes section, this is where we can add in a little bit more information. Our tolerance is set to 40 thousandths of an inch of accuracy. We're making a longboard, it doesn't need to be that accurate, so I'm going to be reducing that to 4 thousandths of an inch. Anytime I'm doing CNC work, as soon as I say I needed this to be incredibly over the top accurate, as the machine is cutting it out, the processor on the CNC may kind of freak out and just pause for a little bit and then, okay, it's fine. What that means in real life is that the cutter stops moving and then continues on. That can lead to burns, which can lead to fires. So reducing the tolerance down to 40 thousandths of an inch is going to be just fine. It's what I do for basically all of my wood CNCing. I also want to be adding on multiple depths. I don't just want to be cutting this out in one pass. I actually want to be going down, cutting the profile, going down a little bit further, and by doing that operation really quickly, I can actually make for a much more efficient cut. So for the maximum roughing step down, it's set to 0.75. I'm going to be changing that to 0.25 so that it's the same value as my diameter of my cutter. We'll be going over why that's important a little bit later in our next project. I can also go into the linking tab, and I want to enable ramping. Ramping basically means that instead of just plunging downwards and then working on the profile, it actually slowly goes down at a 2-degree angle, and it just means that I'm extending the life of the bit, just that little bit extra. But that is basically all we need. You'll notice that our safe distance, because I've added in that ramping, is showing up in red. This is basically saying, hey, your safe distance is lower than what it should be. For this CNC work, I really don't care. If you want to, you can reduce this number, I believe 0.2. Yep, it's gone to black, which means it's perfectly good. It's not really necessary. If you had this at whatever it was, 0.28, for whatever reason. As soon as I click OK, it's just going to give me this warning. Don't worry about that whatsoever. We can just hit yes. So now that we have all of our operations all done and dusted, we can now run a simulation to see exactly what they will look like. So I'm going to go into my Actions tab and select Simulate. And now you can see I've got this whole bunch of information here about how I can tweak exactly how my material is looking. For my tool, I can say, hey, do I just want the tool or the holder, or what am I actually showing? Usually just having the tool in place will be just fine. You can have it transparent if you want. I haven't found that makes it much difference. For the toolpath, if you'd like, you can turn off all the things that is shown. I usually like to see all of the linking. It just makes it a little bit easier for me to understand what the tool is doing. But if you're working on a project where it's more important to see what the final project looks like, and you've got a lot of these lines and it's just kind of hard to see what's going on, then you can turn off your toolpath. That's perfectly fine. Checking out the stock, I usually like to mess around with the colorization, not by what is my operation, but just so it looks a little bit closer to my final project. I'm usually always working with woods or different foams or different plastics on a CNC router, and so having this ceramic where it looks kind of woodish, that's perfectly fine for me. You can have it be transparent, so the stock is a little bit more see-through, but your final project is indeed inside there. Personal preference, you can have that if you'd like. This whole section is just what makes your time a little bit more convenient. If this doesn't look quite right to how you imagine what the CNC is going to look like, that's fine, turn it off. A lot of people prefer to see the tool cutting away the material. That's what they view as a better option. That's fine. The model, you can also adjust the opacity. I'm going to keep it as a full, so I can actually see the project coming out as it's being made. Down here, we also have a play button. Usually it's set way too quickly, so I like to slow it down. And you can see we've got this little green timeline all on the bottom. It's just like a playhead on a video. It's pretty normal, but we can hit play and look exactly what's going on. You can see our drill bit is going down, cutting all the way through. It has in fact made a hole. Let's speed this up just a little bit. There we go, it's going to be moving all the way over, drilling all of our holes. We can actually fast forward or go to the next move if we would like to. We can go to the next operation, which would be our countersink if we'd like. We can speed this up, slow it down, doesn't really matter. Then it's going to flick over to our other tool, which is our countersinking. Then it's going to move over to our end mill. As you can see, if I pause it, this is that ramping operation. It will increase in depth as it goes along. Another really cool thing that I can do is instead of focusing on my model, I can actually focus on my tool. So when I hit play and zoom into it, you can see my tool is cutting around. When I'm doing this type of operation that's cutting all the way through, it's actually a lot easier for me to look at the transparency. So I can see that it is actually going down and cutting through my material. This is now the second level. As you remember, we are cutting this in multiple depths. But as it goes down to the next operation, you'll see that it will start to jump over all of our tabs. So there you go, it bumps up, bumps up, bumps up. I believe we set it to 6 inches. And then as soon as it's done, it'll pop out to say, this is a completed project. We are all done with it. There we go. This is a finalized tool. In real life, as soon as it pops up, this is when the CNC spindle, or the thing that spins, stops, and it will go, or whatever sound effect you want. The other really important thing is if I go over to my statistics tab, we can see this entire project is going to take only 4 minutes to make. In real life, I can see scribing the outer shape, cutting this on a bandsaw, sanding it, checking to make sure it's symmetric, sanding again, going back and forth, punching all of the holes, drilling them out, changing out to a countersink, going through, verifying that they're all symmetric. This might take me 30, 40 minutes perhaps. So I've basically 10th the amount of time that I really need to do this with my CNC, and my final process is going to be much more accurate because of it. And then finally, to export this project, I'm going to be selecting my first operation and going up here to post-process. Post-process just means exporting, basically. When I do this, you'll have a new pop-up where I can name my project. I may want to put number 1 because this is my first operation. Say, yep, 3/16 because that's the size of my bit. And then drill, so I know it's not a 3/16 end mill. You can name these in whatever creative way you'd like. This is just one of the operations that I found works well. You can set what the output folder is, where are these files living. And then most importantly, your unit right here is going to be set to millimeters. Most CNC machines require a file that is set in millimeters. When it receives all the code, it doesn't see move 2 inches, it sees move 2. So by saying this is a millimeter, now everything is scaled perfectly. The other thing you'll notice is that our post, or what is the tool that I'm setting this to, is just set at a generic 2D mill. There's lots and lots of pre-built CNC machines within Fusion. So if you end up getting access to a CNC machine, we go, yay, I get to actually make this project, then they will have a specific post that you can then save into your Fusion 360 library. It's very easy to do, and then you can just select that with this little pull down. So that's perfect. We can just hit post, and you'll see in the bottom corner, NC code successfully posted. NC just means numerical control instead of computer numerical control. Because all of my operations used different tools for all of them, I need to have 3 different files. If I had multiple operations that use the exact same tool, then I can just select all of those and then post-process them all in one big code. But because of that, we would then need to go into Countersink, post-process, and go through the exact same operation. So that is all done for our first CAM project, and we'll be going in a little bit more depth with our next project.